This is the Mathematics Education Podcast from mathedpodcast.com. Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and my guest is Dr. Dana Cox, who's an assistant professor in the Department of Mathematics at Miami University. Dana, thanks for being here.
Thank you so much for having me.
We're going to be discussing Dana's article in the journal Mathematical Thinking and Learning. The article's titled, Similarity in Middle School Mathematics at the Crossroads of Geometry and Number. So Dana, I'm curious with this article, what you see as sort of the main goal or the main issue that this article tackles.
Well, research tells us that very young students have a strong concept imagery about similar figures and scale and are able to reason about proportion to solve problems. For instance, they might view a poster depicting a picture of a dolphin next to a man, and they can reasonably predict whether or not that dolphin will fit in their living room or their back seat in the car.
Mm-hmm.
However, research also tells us that students struggle with similarity, specifically reasoning numerically about scaled images. And even students who can reason proportionally in other numeric contexts don't seem to recognize similarity as a context for proportional reasoning. So I wanted to start to create a bridge for that gap and locate some important, conceptual landmarks in learning to understand scale. And I had some ideas about the role geometric and spatial reasoning might play in that understanding, and I wanted to know more about what made similarity so opaque and why students struggled to reason numerically in that context.
Okay, and so you started thinking about these ideas and noticing the disconnect and wanting to look at that bridge while you were a graduate student, is that true?
That is true. Right away I was invited to be a part of a study group on similarity where we were looking at curriculum analysis and looking at textbooks, treatment of similarity, and that kind of started me thinking about this, but that was also based on my own teaching experience. I had spent 7 years prior to that teaching middle school in Michigan, and I used the Connected Mathematics project for all of those 7 years. Stretching and shrinking was one of my favorite units, and in grad school I jumped at the chance to participate in this forum, I guess.
And so can you say a little bit more about where you did your graduate studies and who you did that with?
Sure. I completed my PhD at Western Michigan University. My advisors were Jane Lowe and Stephen Zebarth, and Jane was the head of that study group on similarity, and she had a major impact on my thinking about the topic. Okay.
I would have you say a little bit more about your dissertation, but actually this article comes from the dissertation, so as we dig into this article from MTL, we're going to have the pleasure of learning a little bit more about what you did for your dissertation study. So you mentioned your teaching experience, and you also were looking at what had been done in the past research literature on similarity. So was there something particular from your teaching or something in your background that really gave you that passion that was needed to go through the entire dissertation experience focusing on this?
Well, I have to tell you a story. We were sitting at the study group and thinking about scale, and all of a sudden I had this watershed moment where I had drawn a heart on the board, and I was telling this story about when I was in 7th grade, and I had drawn hearts all over my folders. And then I'd taken a set of highlighters, and using the highlighter I kind of traced another heart around the original heart, and then using a different color would trace a heart around that one, and another one, and it kind of creates this psychedelic image. For those of you who are familiar with the Powerpuff Girls, it's kind of the heart that's behind their emblem or slogan. And I always experienced this frustration that after I had put about 5 or 6 layers of color on my heart, it no longer resembled the original heart. And I remember feeling frustration as a 7th grade student, and then being with 7th grade students, I saw them doing the exact same thing and expressing the same frustration. So it was like this connection I had with them. But in reality, that's scaling. The expectation that the resulting heart is similar to the original is a context of scale. And it's this visual expectation that we have, and then we can use mathematics to show why that expectation is false. And having that, misconception even in my own thinking that expecting the hearts to be similar, made me think, wow, this similarity has this deep structure to it that fools even a trained eye into thinking that things should be scaled, or not.
Wow.
So, it was really kind of a powerful moment. And then I wanted to know more about what expectations students had about scale and about drawing, and how those expectations influenced whether or not they recognized proportion or not in the context.
Mm-hmm. I've heard, and I remember quite a bit about frustrations related to love and romance in middle school, but you've kind of brought a whole new dimension to that.
I guess so.
So now that you've sort of identified this issue and realized, some of the deep, conceptual factors going on with similarity, and also, that it has to do with this visual expectation. So how did you start to, in a scholarly way, conceive of the geometric side of this sort of proportional reasoning, or the geometric side of these similarity issues?
Yeah, I began to realize that similarity as a geometric context for proportional reasoning was really in a class kind of by itself, and that the rules for reasoning proportionally were different in this context than they were in a numeric context. And I realized that, because of our expectations and because we visualize things, the rules that we learn about number and proportion in numeric context don't necessarily apply to the geometric context. For instance, if you consider the task of scaling a paper clip to twice its size, it's not enough just to make a pile of paper clips. There's no way that you can have enough paper clips that once you have them all stacked, it is a bigger paper clip. So the paperclip becomes as tall and as wide as two of the originals, but it also becomes twice as thick. And you've got to pay attention to not only the height and the width of the paperclip, but also the space between the loops, which is kind of an implicit measurement. So the manipulation of quantities in a problem is not the same as just manipulating how many paperclips we have. It's totally different.
So with the paperclip example, starting with the original and scaling it to twice, it's not a sense of sort of putting another paperclip next to it to get twice the width, and then putting another paperclip above it to get twice the height, and then maybe stacking two on top of each other to get twice the thickness. It's not any of those. It's actually something very different, which is actually getting this new paperclip that's twice as large, twice as thick, and the space is twice. Everything, the explicit and the implicit measures are all now sort of twice their length.
That's right. So that kind of led me to think about a framework for shape, that when we're scaling rectangles, it's enough to scale the overall height and width of a rectangle. Mm-hmm. But when we get into slightly more complex shapes, like the paperclip or the heart, then all of the lengths that we need to attend to aren't necessarily so explicit as the overall height and the overall length. In fact, some of the things we need to attend to aren't even drawn lengths. They are just gaps or spaces within the figure that we need to attend to. Mm-hmm. And so it kind of led me to think about a framework for designing tasks or for analyzing tasks, looking at whether the shape is defined by these primary lengths, which define an overall width or height, or whether there are secondary lengths that we need to think about that are kind of drawn lengths within the figure, but aren't necessarily the overall dimensions. And then also these gap lengths, which are lengths that we need to attend to, but aren't drawn in. There's nothing that says, hey, this is a length. You need to focus on this. And we can look at tasks, so the rectangle would be defined as only primary lengths, or we can design tasks like the heart task, where there are very few lengths that are explicit. And in order to scale a heart, you have to almost completely focus on just gaps. So the height of the heart is not defined as a length. The width of the heart is not defined as a drawn length. It's all just the distance, how wide is a lobe of a heart, or what's the distance between the valley between the lobes and the bottom vertex. They're all kind of these implicit lengths.
So I'm speaking with Dana Cox about her article in MTL called Similarity in Middle School Mathematics at the Crossroads of Geometry and Number. So you pose these research questions about students' strategies when scaling geometric figures, and there's these variety of geometric figures like you were just describing. But also you asked a research question about the forms of the student reasoning, and then you're kind of looking at how that relates to proportional reasoning in general, including the sort of numerical sense.
Yeah. So I was really interested in what kind of student reasoning students applied to these tasks, but then also how the structure of that figure in terms of the lengths that they had to focus on influenced student reasoning.
Okay, so as you started to investigate those questions, what was the data that you collected, or what was the setting for the study?
I had done some prior work in an urban middle school in the Midwest. I'd worked with teachers and students at that school in other contexts, and they, like myself, used the connected mathematics curriculum at the 7th grade. I went in and I targeted all the students that were in sections of one particular teacher. So he had 5 sections of students, and I went in there and used that as kind of my general population. So I administered a similarity perception test to 91 7th graders, which I guess allowed me to select a sample based on their visual perceptions of shape, understanding of correspondence, and understanding of size transformations. And I wanted a sample for clinical interviews that really represented the most common patterns in that arena, as well as the most unique responses. For instance, if a student could not reliably tell just from looking at 2 shapes whether or not they were similar, but then used a functional scaling approach when they were scaling things numerically, that's kind of interesting to me, that disconnect between what they can see and what they calculate using number. So I conducted 21 clinical interviews with students who represented the most common patterns of reasoning and also unique patterns of reasoning.
And in these interviews, you used a variety of tasks, kind of like you mentioned earlier, where there's the primary lengths, the implicit lengths, the gaps, and those kinds of things.
Yes.
So then, of course, we're all very curious. What were the different kinds of student strategies that you saw when you were talking to them about this variety of similarity tasks?
Well, there were a variety of strategies, that's for sure. Some of them have been seen in the literature before, and these are the numeric approaches to scaling. Students use additive reasoning to scale shapes. I think we're all kind of familiar with what that means, is taking a length, adding a certain amount, and drawing a new one. Mm-hmm. And then also functional scaling, which is taking a certain length, multiplying it by a scale factor, and drawing the new one.
Okay.
Another approach would be the unitizing approach. Those of you who are familiar with stretching and shrinking will recognize this from the reptiles lesson. It's taking a piece of the shape as a unit and making copies. If you take the entire shape as a unit, then it creates a tessellation, or reptiles from stretching and shrinking. But you can also just take a piece of the shape and use it as a unit. For example, if you're scaling the heart, you might take just that straight line that comes down from a lobe to the bottom vertex and make a couple copies of it, and then make a couple copies of the one on the other side, and allow that to stand as a scale of the bottom angle. It doesn't work so well with curves. It works with straight lines, but that's unitizing. Mm-hmm. Pattern building. I noticed pattern building is another strategy. Pattern building was the use of patterns without incorporating a functional approach, and pattern building is in the literature already for numeric strategies. In terms of the geometric context, what I saw is, I describe it actually better in the article, but finding the median between 2 rectangles to create one that's kind of in between them. So if you had a small rectangle and a large rectangle, if you took the median of the lengths, you could create a medium rectangle, and that's something I observed students doing. But there were also some geometric approaches that I don't think were as well understood in the literature prior to this. One of those approaches, being a visual strategy, has often been considered primitive or is related to guesswork in the literature. It's also considered non-constructive because it doesn't necessarily lead to a numeric standpoint or a numeric perspective on proportion. It doesn't lead students to think about it numerically. And I think I found that it's slightly more constructive than that from a geometric standpoint. And if we look at similarity from the perspective of geometry, a visual approach is often even more constructive than an additive approach. The student that I really think embodies a visual approach in an interesting way is Elaine. And in the article, I reference Elaine's heart. And so earlier, I talked to you a little bit about my own drawings of hearts and my expectations about what they should look like. And Elaine had the exact same experience. And at one point, she says, sometimes when I draw hearts, I do it like this. And she draws a heart and then draws a larger one kind of framing the original. And she says, sometimes it turns out really well, like this one. This one looks exactly like the one in the center. But sometimes it doesn't turn out very well, and it doesn't end up looking like a heart. And her drawing, the one that she says worked out really well, is this beautiful image of a heart being dilated from a point kind of in its center. And her visual way of drawing a scaled heart really speaks of, I think, a rather sophisticated understanding of correspondence and also a sophisticated understanding of dilation. The heart that she draws, in it's figure 4 in the paper, isn't of a consistent width. So at some points, the width of that frame is wider than at some other points. And what that shows us is that she understands that it's not an additive difference between those hearts. That it's okay if the width is bigger in some places than others because it needs to be in order to be a scaled version. And so this visual approach to scaling the heart, although it doesn't lead her to understanding proportion from numerically, what it does is it shows us that her conceptions of scale are really robust and can be built upon to develop more numeric strategies for thinking about that heart. Had she taken an additive approach and had she simply applied kind of a numeric framework for scaling the heart, she wouldn't have shown that depth of understanding of scale or dilation. And so I contend that visual reasoning is even more constructive than other numeric, strategies.
And it sounds like it could give a very powerful foundation on which to continue to develop the proportional reasoning in sort of all its facets.
Absolutely. Now that takes visual reasoning kind of as separate or distinct from numeric reasoning, but also in the article I talk about a student named Shanice scaling an L shape. So imagine a block L that's represented just kind of in its outline.
Okay.
So you've got primary lengths in the height and the width of that L, but you also have to scale kind of the width of the top part and the width of the foot, or what I think of as the foot. And Shanice started by using a completely numeric strategy. She used an additive strategy to scale the L, and she added 2 to every single side length until she got kind of to the bottom of the top of the foot, and then she realized that her lines weren't going to connect. When she added 2 to the last side length, it didn't connect to the original in the way that she expected it to. And I'm going to pull in that expectation again. And so instead of just being satisfied with whatever happened, she used visual reasoning to apply a fix to that numerically constructed drawing. And so in this way, visual reasoning was really used as a way to reflect on what numerically she had created, to evaluate whether or not she thought it was right, and then to also kind of suggest a fix or a way of mediating what was on the paper with what she expected to be on the paper. And I call that blending because it really blends numeric and geometric reasoning. It's reasoning that's neither totally one or the other. It's kind of a blend, and often students would go back and forth between reasoning numerically and reasoning visually about their drawing. And really that opened up this beautiful space of reflection and evaluation that isn't present when a student blindly or unblindly or rigorously applies just a numeric strategy and doesn't step back, look at what they've created and judge whether or not it's good.
And the issue of additive reasoning, when it's really a proportional situation that sort of calls for a multiplicative type of reasoning, I think having that visual sort of giving credence and allowing and giving weight to the visual approach, if that's a way to help students realize the limitations of additive reasoning and help them take that next step beyond additive reasoning. That seems like that could be a very powerful sort of pedagogical tool as well with respect to similarity and proportional reasoning.
Absolutely. Another really important pedagogical tool that I found in the study was using figures that were defined by more than just primary and secondary lengths. I had students scale a rectangle additively, and then when I asked, is this image similar to your original image, they'd say yes, because they lacked, I guess, the details, or the medium wasn't enough to suggest to them that there was some distortion present.
Right. A rectangle, like a rectangle is still going to kind of look like a rectangle.
Even if it's slightly mushed.
Right,
Yeah.
but if you start to get some familiar shapes where they know what it's supposed to look like, and then when you apply this additive type approach, they'll say, like, no, that does not look right. when you give them a richer type of figure that they can actually tell that something is wrong.
Exactly, and in order to do that, you have to involve some gap lengths, you have to involve some secondary lengths. This L shape that Shanice was scaling was perfect because it created that cognitive tension for her that an additive strategy was absolutely not going to create something that looked like the original.
I'm speaking with Dana Cox from Miami University, which is the Miami University in Ohio, I should say, just to be clear for everybody. And we're talking about our article in MTL, which is Similarity in Middle School Mathematics at the Crossroads of Geometry and Number. And I really encourage people to grab this article because you can see some nice figures and some nice explanations of students' work to really bring these ideas to life. But Dana, I do want to ask you, too, if there's a sort of key or central issue that this work has really left in your mind and that you'd like to share with the listeners.
Well, one thing that really sticks in my mind that I'm feeling kind of passionate about is that we really need to take a geometric lens and apply it to similarity at the same time as applying a numeric lens. Taking a geometric lens opens up the potential for bridging the gaps in student understanding that I described earlier. Early conceptions of scale are entirely geometric and visual, and ignoring that and focusing on using similarity as solely numeric ignores that rich imagery and puts students in a position of kind of throwing out what they already believe and tools that they already have and adopting more procedural ways of thinking. Tom was a student that I interviewed, and at the beginning of the unit on the similarity perception test, he was able to, with remarkable reliability, pick out which figures were similar and which weren't. On the interview, I showed him a picture of two images that were clearly not similar. And Tom identified some lengths within those figures, measured them with his fingers, and determined that, yep, these two figures are similar because I measured the overall height, and there it's twice as big. I measured the overall width, it's twice as big. And he missed some of the distortion that I created by scaling secondary lengths in a different way. And he completely ignored all of his visual tools for determining that these shapes are not similar in favor of these numeric procedures that he had learned in class. And I think if we do that, if we treat similarities wholly numerically, then we're going to end up doing our students a disservice, and we're going to end up, I guess, not bridging that gap between what they could do as small children and what we'd like them to do numerically in middle school.
Dana, thanks for talking about this article. I do have one more question that I like to ask everyone before I let them go, before I let you off the hook.
Okay.
And this is a question, if you can imagine an alternate reality. I'm just curious what you would be doing with your life if you weren't in the field of mathematics education.
Well, wow, that's a good question. It's easier to answer than the other one, which is what ice cream flavor are you? What would I be doing? If I really use my imagination, I think I would be the proprietor of a small yarn boutique store where people could come and knit, and people could come and be together as they worked on yarny kind of projects. I'm an avid knitter, and I would love to be around other people who do that too. During graduate school, one of my favorite things was a weekly knitting group that met over dinner, and I tell you, that relieved so much stress for me, is being around those people.
Wow. Yeah, and I know I've been to some conferences recently where there will be at least one or two folks knitting throughout a conference presentation, and I think, they say it helps them actually concentrate on what's being presented by just having that in their hands. And
Yeah.
do you know of any boutiques like that where they do create that space to come and knit?
I do. There are some actually located here in sunny Ohio, if anybody wants to come visit us here.
Wow.
I say sunny Ohio because it's sunny today, but it isn't often.
Dana, thank you so much for being my guest and for talking about your work.
Thank you so much for having me. It's been a pleasure.
Thank you for listening to this episode of the Math Ed Podcast. If you'd like to support the podcast financially, please use the PayPal donation button at mathedpodcast.com.